So who is this Kirchhoff anyway? Gustav Kirchhoff, also pronounced Kirchhoff, was a German physicist who contributed to fundamental understandings of electrical circuits, spectroscopy, and the emission of blackbody radiation by heated objects. Alright, so his first law, remember, was current going in to a junction has to equal current going out of a junction. His second law is the sum of the voltages, or potential differences, provided must equal the voltages dissipated across the components. So what that means is, as charges go through a circuit, they get energy from the battery, and then they give away energy to the components. Well, when that happens, there is a gain in potential difference as they get more energy, and then as they give away more energy, there is a drop in potential differences. So there's a gain over batteries and a drop over resistors. If you follow the path that the current goes around the circuit, it will always equal a potential difference of 0. Okay, so if we were to follow the current from here, going from the high potential to the low potential, over here, whatever this resistor is, whatever this resistor is. Okay, so when it comes over, it gets to this resistor. How much is it going to drop? Well, over here we know there's going to be a drop of 8. So this is a gain and this is a minus. So 12 minus 8 means that this one is 4. So we start off with 12 volts, we lose 4 volts, we lose 8 volts, charges come back to get more. Over here, we start off with 12 volts, we lose some amount, let's say, we lose 1 plus 9 is 10, so this must mean there is a potential difference drop of 2 volts. All right. Across batteries, from negative to positive is positive. If we go positive to negative, then it would be negative. Over resistors is always negative. And so that's not going to specifically affect your problem solving here. As you'll see, if we started with 12, positive 12, we lost 8 over the resistor, and then we lost 4, adding them all up. Same thing over there. How difficult is it for electrons to flow? Resistance. The symbol for resistance is capital R. The unit is ohms. The symbol that we use for the unit is the Greek letter omega. Ohm and omega. So which has more resistance for water flow? Is it this skinny little hose, or is it this big, huge pipe for oil? Well, if it's smaller, probably going to have more resistance. Conductors have a low resistance, insulators have a high resistance, as a review. More review on resistance. We have copper's valence electrons, so we're looking at a copper wire. The valence electrons move freely throughout the solid copper metal. That's what allows for conductors to work, is the electrons free to move. All right. There are many different components that act as resistors when placed in a circuit. And here they are here. We have a normal resistor. We have a variable resistor, which will allow us to change the resistance. We have a potentiometer, which will alter the potential difference. We have a normal lamp. We talked about all of these before. A light-dependent resistor. As more light hits the resistor, it's going to resist less or more, depending. Thermistor is temperature reliant, and you may see the resistor as any of these, or it just might be a little squiggle. All just means energy is being transformed from electrical to some other. All right, so we have voltage. is the property potential difference, given as V, volts. Another property is current. Current is the rate at which charges move through the wire, the flow. The symbol is I. The unit is capital A for amps. Resistance. How hard is it for a current to flow through a conductor? Capital R. And the unit is the ohms, omega. Go look at some of your electrical appliances in your house. Look at the plugs on any of your transformers, the bricks that charge your cell phone. Look on there. There's a sticker. You'll see some of these symbols. You may see omega. You may see watts. You may see volts. All right, so how are those three properties related? Well, if voltage goes up, current goes up. Voltage is proportional to current. If resistance goes up, that means current goes down. Resistance and current are inversely proportional. There's a little picture for you. You have the ohm, the resistance, squeezing this tube so the current can't get through while the voltage is pushing to try to give it that energy to get through. Memorize Ohm's law. It's a mathematical relationship between the electrical properties. V equals IR is the common way to remember it, just because it's all multiplication, and that's nice, and it's not a fraction, so it's not scary. On your data booklet, you'll see R equals V over I. The law was named after the German physicist, again, George Ohm, who in treatises published in 1827 described measurements of applied voltage and current through simple electrical circuits containing various lengths of wire. Ohm explained his experimental results by slightly more complex equation than the modern form. Listen, Ohm's law, V equals IR. You may even remember it from past science classes. This law is only accurate and effective if you have a constant temperature. If you don't have a constant temperature, then the resistance normally will go up. So you have to remember that this all has to be in a situation where the temperature is constant. R is the resistance is constant, independent of the current. If the resistance is not constant, the previous equation cannot be called Ohm's law. Here's another form of Ohm's law, which solves for everything, including power. Remember, power is just the rate at which energy is used. So we have power measured in watts still. I is amps, R is ohms, V is volts. So these are just all the different forms. So if we're looking for voltage, it could be power over current. It could be resistance times current. It could be the square root of P times R. If we're looking for power, power is just your voltage times your current, or it's resistance times I squared, or it's voltage squared divided by R. Those are your rates that your energy is consumed. If we're looking for resistance, it could be any of these forms, all derived from that first V equals IR.